and welcome to Physics 11 Kinematics Lesson 3, Graphing and Uniform Motion. Before we start talking about uniform motion, we need to talk about some graphs. Every graph you have has three key parts that you must include. The first part is the title. The title of a graph tells you what this graph is about without having to look at the graph itself. This should be a quick overview of what the graph is talking about. The second most important part of a graph are the axis labels. You need to tell the reader what your axes are. Without a label, your measurements have no meaning. The third most important part of the graph is your axis scaling. You need to tell your reader what each line signifies. With no axis scaling, a reader can understand the general trend of your graph, but will not see exact information. In physics, graphing is very important as it can give us a quick glimpse of the motion. You can see any trends that are happening without having to look at all of the numbers individually. Some key points of the graph are axes, intercepts, and slope. We will look at each one individually. First, axes in physics. All graphs have a horizontal and a vertical axis. The horizontal axis is called your x-axis, while your vertical axis is called your y-axis. The horizontal axis typically will give the independent variable. In simple titles, this is your second value, and for physics, this will generally be time. Your vertical axis gives the dependent variable. In simple titles is the first value, and for physics is generally position or velocity. However, the axes could be any two values, so you must look at the labels before you look into the graph itself. In this example, we have a y-axis of position and an x-axis of time. This graph, however, is not complete. It is missing a title. A simple title you can give is a position-time graph, since your y-axis is position and your x-axis is time. If your x-axis was position and your y-axis was force, that graph could be called a force-position graph. Again, you are naming a y versus x graph. Our second area of interest is the intercept. Intercepts give you the zeros of your graph. Specifically, the y-intercept tells you where your line crosses the y-axis. Generally, for physics, this gives you the initial conditions. What was the object doing when time was equal to 0? The x-intercept depends on which type of graph you have. For a position-time graph, the x-intercept tells you when the object returns to origin, or where you are measuring from. In a velocity-time graph, this tells you when does the object stop, or when is the velocity equal to 0. In this example, you can see the y-intercept is 50 meters. This graph started measuring this object when it was 50 meters away from the reference point. The x-intercept is 5 seconds. So this object reached the reference point after 5 seconds. Our last point of interest is the slope. Looking at a position time graph, we know that the slope is equal to the rise over the run. Specifically, on a position time graph, our rise is our displacement, and our run is the time interval. Displacement over the time interval is equal to our velocity. Therefore, the slope of a position time graph must be equal to velocity. If you have a position time graph of an object, you can find the velocity simply by finding its slope. Recall that a slope may be positive or negative. The sign does make a difference. It changes the direction of your velocity. A positive slope would indicate that your velocity is moving in the same direction as your graph. A negative slope would indicate the object is moving in a negative direction of your measurements. Returning back to this graph, we can find the velocity by looking at the slope. We know that the slope is equal to the rise over the run. This object has moved from 50 meters down to 0 meters, so our rise is minus 50 meters. This object started at 0 seconds and moved to 5 seconds, so our run is 5 seconds. Therefore, the slope of this graph is minus 50 meters over 5 seconds, which gives minus 10 meters per second. Therefore, the speed of this object is minus 10 meters per second. Remember, a velocity is a vector, so we need a direction. So the velocity of this object is minus 10 meters per second up. Or, more simply put, 10 meters per second down. Now that we have looked at graphs and understand how we can read the motion from graphs, we may start to look at uniform motion. Uniform motion, as the name implies, is motion where the velocity remains constant. Here, uniform means unchanging. On a position time graph, a constant velocity is shown when the slope is constant, and a constant slope indicates a straight line. Any straight line on a position time graph implies a uniform motion. Here we have two examples of position time graphs. In our first graph, the data is a straight line. This indicates that this is uniform motion because the slope is not changing as we increase in time, so the velocity is staying the same. In our second graph, the slope is changing as we move forward in time. This means the velocity is changing, and therefore this is not a uniform motion graph. Is this graph uniform motion? In this case, yes, this graph is uniform motion because the velocity is not changing. It is a straight line. A constant velocity of 0 is still a velocity, and this indicates uniform motion. Is this a uniform motion? Here, this graph, the slope changes 2 times. There are 3 different slopes in this one graph, so this is not uniform motion. But does it have uniform sections? In this graph, we may not have uniform motion overall, but if we look at only 0 to 20 seconds, that is a straight line. If we look at only 20 to 30, that is also a straight line. And from 30 to 40 is also a straight line. So this may not be uniform motion, but it has uniform sections. Parts of this motion are uniform, and if we break down this motion into 3 pieces, we can understand the motion better. Here, it is easy to find the velocity from 0 to 20. From 0 seconds to 20 seconds, the slope is a rise of 50 over a run of 20. This gives us a slope of 5 over 2, or a velocity of 2.5 meters per second up. Even though only sections of the motion are uniform, if you want to look at the average velocity, you can look across different sections. For example, what is the average velocity from 10 seconds to 30 seconds? Remember, velocity is a rate of change of displacement. Displacement does not care of the actual path taken. It only cares of your final conditions and your initial conditions. Therefore, to find the average velocity from 10 seconds to 30 seconds, we can very easily find our change in displacement over our time interval. Our change in displacement is equal to our final position minus our initial position, and our time interval is our final time minus our initial time. Here, our final position is 100 meters, and our initial position is 75 meters. Our final time is equal to 30 seconds, and our initial time is equal to 10 seconds. Here we find 25 meters over 20 seconds, and this gives us a velocity of 1.25 meters per second. With significant figures, we see that this must be 1.3 meters per second. Because this is a velocity, you must add a direction. There is no direction given in the graph, so we will put in forward. Similarly, what is the average velocity from 20 seconds to 40 seconds? Well, we know we only need our final position and our initial position. Our final position is 0 meters. Our initial position at 20 seconds is 100 meters. Our final time is 40 seconds, and our initial time is 20 seconds. Here we can solve this to find 100 over 20, which is equal to minus 5 meters per second. Remembering significant figures, this gives us minus 5.0 meters per second with a direction forward. However, in physics, we do not like to have negative values as much. Although it is correct, it is not as pleasant. So we can change minus forward into positive backwards, and this becomes 5.0 meters per second backwards. This is all for this lesson of graphing and uniform motion. Thank you for watching.